Welcome back. So, we were continuing our discussion on orbit, and in the last session we talked about how to raise the orbit using thrusters at apogee and perigee, and if it is not launched from the equator location, then how to correct that inclination and reach to geostationary orbit. Now, at geostationary orbit also we have seen certain perturbation due to the other bodies and due to our assumptions which initially we have taken for orbit, and for that certain corrections are necessary. Orbital corrections are necessary on the satellite. For that we have to spend some fuel, and we have estimated that some fuel should be left, that when the fuels are exhausted, the electronics may be live and will be communicating, it will disturb others, and the orbit will be slowly drifting in east west and north south. Therefore, it will have interference to other operating satellite. Therefore, it is deorbited, that is, it is put in a different orbit using that extra last amount of fuel, and that is the end of the satellite life. That is how we define, though the electronics of the satellites are not dead. Now, let us see at this geostationary orbit what are the effects that we have to consider for our communication. Let us look at this. Some of them I listed here, that is the effect on the communication system by variation in the range, that is the distance d from the observer, that is Earth station to the satellite. There is some effect on the solar eclipse, there is some effect on sun conjunction, some effect on Doppler, and many other. These four I have just picked up. Let us see each of them. Simple geometry. It is a circular orbit, 1000 kilometer orbit height, and there is a overhead pass. You can find that for a observer here, what will be the distance when the satellite is overhead or when the satellite is rising. Let us say it is rising, it is going in this direction. So, that means 0 degree inclination elevation or 90 degree elevation. If it is 1000 kilometer orbit height and assume Earth as a sphere, and as we were talking about 6378 kilometer as the Earth spherical radius, you can calculate what will be the distance. The other thing is solar eclipse, that is Earth's shadow on the satellite, that will reduce the satellite power generation, and during that period the battery on board has to be used to supply all the power to the electrical circuit which are on board. Let us look at it. Look at this geometry, that is assume that this is Earth, and though Earth is rotating around the sun, and this is the orbital plane which is equatorial plane, and satellite is here. So, we have seen that it makes 23 degree angle with the Earth orbiting plane on the around the sun. If we can draw it differently, you can see that as if sun is apparently moving north and south over the year. So, when it is going to the extreme north is one summer solstice, when extreme south winter solstice, and when it is on the equator same plane is called equinox. You can see for northern hemisphere these are the summer period, this is the winter period when sun goes south. But then the Earth's shadow also will be moving over the period, that is year. As sun goes top, the Earth's shadow will be towards this plane which is away from the orbital plane. So, therefore, Earth shadow will not fall in the satellite. When the Earth shadow will fall on the satellite? When it is near equinox. let us I have drawn another picture where the satellite is shown here, and this is the equatorial plane, and sun is come on the equinox, sorry, on the solstice, coming towards the equinox. At some point of the year, some day of the year, the shadow of the earth will start falling on the satellite, and that will happen sometimes in the night, isn't it? That is, this side, those who are communicating with the satellite, for them this is the night, and then sun is further going down and down. So every day towards the night, the satellite will be shadowed by earth for some period of time. It has been seen that this eclipse period, the earth's shadow falling on the satellite, is 22 days before and 22 days after equinox, roughly. These are all rough numbers, and it happens end of February to mid-April during summer, and during winter the other direction also similar thing will happen, August to mid-October roughly. And at the middle of the time, sun shadow, earth shadow is fully covering the satellite at the mid of the night. And how long this duration? The shadow will remain on the satellite during the night, when the sun, earth center and the satellite are on the same line. We have seen the other session, the calculation, that is satellite to earth, this angle, visibility angle, was 17.4 degree. By this figure you can make out that the same from the center of the earth, same 17.4 degree will cover from here to here, that is the shadowed period. So as the earth rotates, the satellite also rotates like this. So what is this duration? That is a fraction of 360 degree, 17.4 degree fraction of 360 degree. So maximum duration of the eclipse is 17.4 by 360, and the earth is revolving one-sided real day 86164 seconds. In terms of minute, it will be roughly about 70 minutes. So for 70 minutes period in the night of during those days, when the sun earth's shadow fully falls on the satellite, this is the duration during which the satellite will not get sun, and its solar panels will not get will not be able to generate electricity. During this period, it has to operate on battery. So power system of the satellite will come into picture. The other side, that is when the daytime, the sun is behind the satellite. Just imagine, this was earth was between satellite and the sun, and in the daytime, in the same period of the year, the sun conjunction takes place, which is that local day sun comes behind the satellite, and the receiver station gets a very wide band microwave noise which is generated by the sun in addition to the signal generated by the satellite. So that noise will bury the signal. This sun noise temperature is roughly about 6000 K to 10,000 K, rough numbers. The signal gets buried in the noise. Now this can be calculated how much it is, and during that time the link will be out. What is the time? It is the relative movement, that is east-west movement of sun is 360 degree by 24 hours 60 minutes, which is 0.25 degree per minute, as if sun is moving, actually earth is moving. And if the satellite earth station antenna beam width is theta, so sun will remain within the antenna beam for the duration theta by 0.25 degree per minute, that is 4 theta minute. And the temperature is expressed in a formula like this, that is delta T is equal to P and eta and Ts and ds square each is explained like P is a polarization factor. This is a new terminology, polarization. Those who are familiar with the RF, they will know what is polarization. Is the electric field vector, and since it is generated in randomly and antenna is pointing to one particular electric field vector, this is assumed that 0.5 value is taken. It may not be aligned with the noise which is coming, so a 0.5 value is taken. Eta is the efficiency of the antenna, and Ts is the temperature of the sun, which is depending on different frequency. Roughly a model is given 0.12 into 10⁶ f to the power minus 0.75, where f is in gigahertz, and ds is the equivalent sun disk with respect to antenna beam width theta, that is ds is 0.48 by theta for theta is equal to greater than 0.48 degree, and 1 for theta equal to less than 0.48 degree. These are some rough numbers. So, on this basis some calculation of the temperature can be made. There is another phenomena which is called the frequency or Doppler shift, that is due to transmitter velocity component towards the receiver. All of us know that is the difference of the frequency, that is transmit frequency, and actually the change in frequency, that is delta f, by the transmit frequency is the velocity towards the receiver, transmitter velocity towards the receiver by the velocity of light, and you can put it in terms of lambda also, that is the delta f is Vt Ft by c or Bt by lambda. Now, this Doppler shift is for GSO, it is negligible. For low Earth orbit satellite, a frequency tracking receiver is needed to mitigate this Doppler shift. So, with very briefly speaking, we have seen that there is for different orbital effect on communication system can be listed like this, that is the range variation which will affect the time. It is important in the communication system when we talk about the multiple access, particularly time division multiple access, that is many people are trying to access the satellite resource, and each person, so that they should not interfere with each other, allotted different times, and that means their signal should reach the satellite at the allotted time. Now, as the distance from the transmitting stations to the satellite varies, the signal will may not be able to reach in the allotted time. So, that adjustment is very, very important. Also, we will see much later that this physical variation of the time can create the delay in the reception of the signal, and whether signal is received correctly or not will be seen by the acknowledgement of the signal from the receiver. And as this delay varies, there is a technique called retransmission on positive acknowledgement, on non-reception of positive acknowledgement. So, that retransmission time varies. We will see in the satellite channel effect on higher layer, that is on TCP layer, this range variation can create a major problem. We'll do the calculations later. So, you see the range variation to the affected, which is affecting as a time, is in terms of TDMA and higher layer effect that will come. The other one is a solar eclipse. We have seen that Earth's shadow falls on the satellite, so the power generation is reduced. it is not only the power generation, the thermal imbalance also takes place. When the satellite is, one side is exposed to the sun, that side is having some temperature, other side is having much lower temperature. Temperature gradient is different. When the shadow falls, the temperature also changes. So there are double effect. One is the battery has to take over during that time, and second is the thermal imbalance. The solar eclipse creates a problem, and of course initial days satellites which were not able to carry highly efficient and large amount of battery, many of the amplifiers used to be switched off. Fortunately, this happens during the midnight time, around midnight time. Earlier days television and many other communication were not taken at the local midnight time, but nowadays it is all 24-hour service. So therefore this is very important, and larger size of battery are launched along with the satellite to take care about the solar eclipse. The opposite effect is in the same time of the year, the daytime, noon time, the noise falls on the receiver if it is in line with the satellite and sun. Noontime, it depends on the time period, and again people have tried a different sizing of the antenna, because it depends on the beam width of the antenna. If it's a large station, beam width is smaller. We have seen that effect will be more. It can be calculated using that formula what I have shown you, that with a different beam width of the antenna, how the noise varies for a particular frequency range. Then of course the Doppler, that for geostationary satellite, the Doppler effect is much less, though we have seen that for station keeping, within the station keeping box, the satellite moves here and there, and for very high bit rate communication, where the bit duration is less than microsecond, let us say 100 megabits per second or 120, 150 megabits per second when it's being communicated, the bit duration is very small. So therefore that drift of the satellite that has some effect on synchronization. So that is in GSO, though it is not much affecting, because very few communications takes place at a very high bit rate. But for low Earth orbit satellite, this is important because the Doppler has some effect. Of course, it depends on the frequency. You should be able to do some calculation on based on different frequency and different orbital height of that. In the textbooks, like in the Pratt, some calculations are given there. So these are very briefly some of the orbital effect on the communication system. So till now, let us recollect what are the things we have seen. What was covered is from the beginning in these 4 sessions, we have covered the orbital period, the velocity and the orbit, height, their relations in the circular orbit, in the elliptical orbit, and also how to find the location of the satellite, and based on the very commonly used term for geosynchronous satellite, defining the latitude longitude as a sub-satellite point as the satellite location, though in the actual coordinate it will be much different. The visibility of the satellite from the Earth station is calculated, and we have seen that how to calculate that elevation and azimuth angle, and also we have seen how to calculate the distance from the Earth station to the satellite, which is very important to us. We have also seen that how this geostationary orbit is achieved. by initially putting into parking orbit, and by giving different thrust to put from parking orbit to geosynchronous transfer orbit, and then from geosynchronous transfer orbit to the geosynchronous transfer orbit, which is elliptical orbit, to the geostationary or geosynchronous orbit, which is a circular orbit. So these incremental velocities we have done with a rough, some rough calculation. And then also we have seen that as geostationary orbit is supposed to be zero inclination with orbital plane with the equatorial plane, and in real life may not be able to launch from the equatorial plane. The launch sites are at though they are near equator, they are away from the equator. So this launch latitude and their elevation azimuth angle of the launch, these are related to put into different inclination of the satellite orbit, and how to correct that inclination to the geostationary orbit inclination. That expression we have derived, and we have seen that. Then subsequently we have seen what are the different perturbation that takes place in the geostationary orbit particularly, and low Earth orbit in some cases. That is basis of the assumption what we had initially, the Earth is a sphere and there is no other body around, and forces acting are on them except Earth and satellite, nothing else is there. Though in real life Earth is not sphere, its density is not same, and it has a different gravitational force at different location. So therefore certain stable and unstable points are there in the geostationary orbit, and the effect of this perturbation, any perturbation on the geostationary orbit, will drift the satellite in east-west direction, which needs to be corrected. Similarly, Sun and the Moon is also not in line with the Earth equatorial plane where geostationary satellites are put. So therefore the gravitational force acting on the satellite by Moon and Sun varies depending on the day, on the particular time. Therefore the effect of that on the geostationary orbit is northward or southward pull of the satellite. So this is called north-south movement, and these perturbation is to be corrected. Otherwise many satellites are possible to be placed in geostationary orbit, which will start drifting and the signals will start interfering. Remember that they may not physically collide because the distances there are very large in kilometers and satellite size is very small, few meters square, but the signals will collide. So therefore there will be a lot of interference. To avoid the interference, the international bodies like International Telecommunication Union, they have defined that satellites to be kept within a particular area, a particular volume, which is called station keeping box. Brief description of the station keeping box for different frequencies are given. Why different frequencies? At different frequencies different lambda will be there. So it's given in terms of angles. You can calculate the distances of that, but these are very approximate. And the operator, satellite operators, they try to keep the satellite within the station keeping box for that particular satellite, allotted satellite, and for that they have to, based on east-west and north-south movement of the satellite, they correct by firing from the opposite direction the thrusters, and keep the satellite within that. And if the satellite is in the low Earth orbit, then there will be a lot of perturbation on the satellite because of the atmospheric drag. I forgot to mention that there is a solar radiation pressure that comes on the satellite. In addition to the generation of the electricity, it provide the pressure on the surface which is facing to the sun, particularly the larger surface which is solar panel. So because of that there are some movement, and we will see during the spacecraft discussion, the solar panels are north-south oriented with respect to Earth. So therefore, it's a north-south tilt will be there, and that also has to be corrected. For low Earth orbit satellite, the atmosphere will start affecting, though the satellites are not orbited in dense atmosphere, that is roughly about 800 kilometer. So satellites are kept normally at higher than that, that is 1000 kilometer. But lower orbit satellites lower than that can create heat over the satellite and on the satellite, and it may burn. So therefore, this atmospheric drag change the satellite orbit height, and slowly it drifts down. In addition to that, that movement of the satellite, we have seen that there are many communication effect on the communication system on the satellite. One of them is delay, depending on the position of the satellite. For geostationary satellite, delay will be same for a fixed station. For low Earth orbit satellite, it will be varying, and for mobile station, of course, the delay will be varying for both the cases. And then there is this power generation problem when the shadow of the Earth comes on the satellite. Then and there is a noise problem when the sun is behind the satellite. This happens in a particular time of the year. And of course, for low Earth orbit satellite, because of its movement speed with respect to the observer or the user on the Earth, there will be some Doppler effect, and that has to be corrected for our communication system. So these are briefly we have talked about during our orbit topics. In the books, referred books like Pratt and Marall and many others are there, where orbital much more details are there, derivations are available, you can go through there. Our interest is to is for you to know the knowledge of the communication system effect on the orbit. With this, we close this particular topic, and we'll go into next session into the space segment, what is there inside the satellite, that we'll discuss, and mostly we'll concentrate on the communication part of the space segment. Thank you very much for listening. We'll give you some assignments, and based on whatever we have discussed here, you use your intelligence and try to answer those assignments. Thank you very much.